where he has done his master's from here, and
Yeah.
he works on quantum information, quantum cryptography, and entanglement. He has worked on that, and today he's going to tell us about polar codes.
Yes. Thank you for the
Over to you.
introduction. Yeah. Okay. I'm going to talk about purely and multi-level quantum polar codes. They are basically a family of quantum error correcting codes. And this is basically based on these two papers, which are on archive. And this is joint work with Frederick Dupuy, Mehdi Mala, and Valentin Salim. Okay, and so first I'm going to give like some context about polar codes in general, like about classical polar codes, and some context about quantum polar codes. So imagine two friends, Alice and Bob, who are calling each other on their telephone, but the telephone line is like so noisy that they cannot like properly hear each other. So now how do they deal with this problem and communicate in a meaningful way? So in other words, Alice and Bob, they share a communication channel which is noisy, and they want to communicate reliably using this noisy channel. Yeah, here the noisy channel is basically represented by W here. And thanks to Shannon's discovery back in 1948, we know that it's possible to communicate reliably using noisy channel by exploiting error correcting codes. So this is a sketch of error correcting code. So at the transmitter end, we have an encoder which encodes a k-bit message into n-bit message, where n is greater than or equal to k. And then this encoded message is transmitted through the channel, through the noisy channel. And at the receiver end, we have a decoder, which after receiving the channel output, the decoder tries to guess the input message U. So basically it outputs an estimate U hat. And what we want is that, like, what would be ideal is that U hat is equal to U with very high probability. And the error probability of this error correcting scheme is defined as the probability when this symbol U hat is not equal to U, basically when your guess is wrong. And the rate of transmission is defined as here the k divided by n. So k is like the length of the input message, and n is the length of encoded message. And there is basically an upper bound for a given channel on the rate of transmission, which is called capacity. So like in more formal language, the capacity is defined as the tightest upper bound on the achievable rate of transmission. A rate of transmission is called achievable if you can like transmit at this rate with arbitrary low error probability. And according to the Shannon's noisy coding theorem, the channel capacity is given by the mutual information. As you may know, mutual information is a measure of correlation between the input and output of the channel, and it takes values between 0 and 1. And when If for a channel the mutual information is equal to 0, that means the channel is kind of useless. You cannot use this channel to transmit any information. And if mutual information is equal to 1, that means that it's a perfect channel. You can basically transmit information perfectly through this channel. Just to say that, feel free to ask questions if you have any in the middle. Yeah, feel free to stop me. So when constructing an error correcting codes, basically these are two expectations. Basically these two properties are desired. The first is that that your code operates close to the channel capacity, and the second is that your encoding and decoding is efficient. And Arikan, he introduced polar codes in 2009 after 60 years of Shannon's noisy coding theorem. And these codes are in fact the first family of codes that provably achieve the channel capacity. And they have efficient encoding and decoding in the sense that the complexity of encoding and decoding is log linear. So I am going to briefly give the main ingredients of polar codes here. So here I consider binary input channel. So basically the input alphabet of the channel is binary. Polar codes are based on something called a channel combining and splitting procedure. So this here we have the channel combining for two instances of a binary input channel. So we have two instances of W. So this is how channel combining is done. We have inputs U0 and U1. We first apply like a reversible XOR gate on the channel input. So this gives us the output of the XOR gate is U0 plus U1 on the first wire, and on the second wire we have U1. And then we basically transmit this. After applying the XOR gate, we transmit this X0 and X1 through the binary channel. And after basically this, you can see this as like a combined channel. So the combined channel is W2. It takes as input U0 and U1, and it outputs Y0 and Y1. Now, then what happens is like the combined channel is split into so-called virtual channels. So these two virtual channels are bad virtual channel W0 and good virtual channel W1. So I'll explain why this one is called bad and why this one is called good. So for the bad virtual channel, the input is U0 and the output is Y0, Y1. And the second wire here is kind of not known. The value here U1 is not known. So we have the input U0 and output Y0 and Y1. And for the good virtual channel, we have input U1 and output U0, Y0 and Y1. So for this one, we have basically a copy of this. The first input is given at the output. And now this channel combining and splitting is basically applied recursively. In this figure, you have the channel combining and splitting for 3 levels of recursion. And on the left-hand side, you have 8 basically synthesized virtual channels. So basically these virtual channels are, in a sense, like just looking at the input and output in a different way, you can say. Now, this is Arikan's channel polarization theorem, which states that as n goes to infinity, basically as you take many levels of recursion, for example, after n level of recursion, we have 2 to the power n virtual channels. And Arikan's polarization theorem states that as n goes to infinity, almost all the virtual channels, they become either completely noisy or completely noiseless, in the sense that their mutual information either goes to 0 or goes to 1. So to summarize, we started with n instances of a noisy channel W, where n is a power of 2. And then these n instances of W are converted into so-called virtual channels using a channel combining and splitting procedure. And for these virtual channels, we have this polarization effect, in the sense that they are either very close to being completely noisy, or they are very close to being completely noiseless. And basically the idea of polar codes is to use these noiseless channels for communication. And somehow we need to fix the input of these completely noisy channels, because their inputs are kind of needed to decode the information at the receiver end. So the input of these completely noisy channels should be known to the decoder. And polar codes have an efficient decoder, which is called successive cancellation decoder. And the successive cancellation decoder basically makes estimates on these completely noiseless channels. So polar codes have also been generalized to the quantum setting. For example, in this paper, we have polar codes for classical quantum channels, where the input is classical and the output is quantum. And in these 2 papers, we have polar codes for quantum channels, where both the input and output is quantum. However, for this quantum generalization, polarization phenomenon is basically based on this classical quantum channels. So for these quantum polar codes, what happens is, like, first the quantum channel is kind of split into 2 classical quantum channels. So here we have the first one, WA, which is basically obtained by acting the quantum channel N on a amplitude basis state. So basically, you input a classical either 0 or 1 state to the quantum channel, and this gives the classical quantum channel WA. And similarly, in the phase basis, you input either plus or minus state, and this gives another classical quantum channel WP. And basically, this quantum polar codes uses a channel polarization phenomenon for this classical quantum channels. Now, what we did is proposed a purely quantum polar codes, for transmitting quantum information, which is basically based on a polarization phenomenon for quantum channels. So in a sense, this polarization phenomenon happens at the quantum level and not just in a basis. And these purely quantum polar codes require pre-shared EPR pairs. And so these codes also have efficient decoding for qubit Pauli channels, and the property which is called fast polarization. This I will not discuss here. And for Pauli channel, we also have a slightly different kind of polarization phenomenon, which is called multi-level polarization. And this multi-level polarization allows to reduce the number of pre-shared EPR pairs. Okay, so I will start with purely quantum polar codes for quantum channels. So first I will say a few things about quantum channels. So quantum channel describe the dynamics of an open or a noisy quantum system. So in this figure, we have a quantum channel N, which takes as input quantum system A and outputs another quantum system B. And mathematically, this quantum channel N from A to B is a linear map from the set of linear operators on the Hilbert space of quantum system A to the set of linear operators on the Hilbert space of quantum system B. And this map is completely positive and rest preserving. Symmetric coherent information is a measure of quantum information for the quantum channel. So basically, symmetric coherent information tells whether the given quantum channel, basically how good the given quantum channel is. So to define symmetric coherent information, we need EPR pair. As you may know, EPR pair is a maximally entangled quantum state on 2-qubit quantum system. And to define this symmetric coherent information, what we do is like we apply quantum channel N on one half of an EPR pair. So here the EPR pair is denoted by phi A prime, and we basically apply the quantum channel on A prime half. And on the other half, we have the identity. Now this gives us a quantum state rho AB, and symmetric coherent information is defined as the difference of one Neumann entropies of system rho B and rho AB. So rho B here is basically the partial quantum state of system B, which is obtained by tracing out the system A. And this symmetric coherent information takes values between -1 and 1. And if for a given channel it is equal to 1, that means the channel is a perfect quantum channel, in the sense that the channel output is same as the channel input. And if for a channel it's equal to -1, that means the quantum channel is like a erasure channel, which completely erases the input quantum information. So basically, if you input a quantum state rho, the output would be a completely mixed state. And I will also need the definition of Pauli and Clifford unitaries. So I will briefly recall them. So single qubit Pauli unitaries are a set of 4 unitaries, identity X, Y, and G given here. And single qubit Pauli unitaries multiplied by a phase factor of either plus minus 1 or plus minus I form a group in mathematical sense. An n qubit Pauli group can be obtained simply by doing the tensor product of single qubit Pauli group n times. And this n qubit Clifford group is a set of unitaries that basically generate permutation on the Pauli group by their conjugate action. So basically this means that if you conjugate a Clifford to a Pauli, you will get another Pauli. Okay, so now I come back to purely quantum polar codes. So to construct purely quantum polar codes, again, we need this channel combining and channel splitting procedure as similar to the classical case. And we apply this channel combining and channel splitting recursively on many copies of a quantum channel. So this is channel combining here. On the top, this is channel combining for 2 instances of a quantum channel. So basically, what happens here is like we have 2 inputs A1 prime and A2 prime. And on these 2 inputs, we first apply a Clifford unitary, a 2-qubit Clifford unitary. And then the output of this Clifford unitary is transmitted through the quantum channel. So you can see like to make a comparison with the classical case, in the classical case, we had a XOR gate here. And in the quantum case here, we simply replace the XOR gate by a Clifford unitary. And we can see this as a combined quantum channel. So whose input is A1 prime, A2 prime, and output is B1, B2. And this combined channel is again split into 2 virtual channels, which are called bad virtual channel and good virtual channel. So for bad virtual channel NC0, we have the input A1 prime and output B1, B2. And for the second wire, again, for the second wire, the input is completely mixed state here. So it's like the second wire has been kind of erased in some sense. And for the good channel, the input is A2 prime and the output is A1, B1, and B2. And for the first wire here, what we have is like a pre-shared EPR pair. So for this EPR pair, its A1 half is given to the receiver, and its A1 prime half, this goes through the channel combiner. Again, for this channel, virtual channel NC1, the input is A2 prime and output is A1, B1, and B2. Now, it's worth noting that the symmetric coherent information is preserved under this channel combining and splitting, meaning that the sum of the symmetric coherent information of the bad and good channel is equal to the twice of the symmetric coherent information of the original channel. And also the symmetric coherent information of NC1 is greater than or equal to the symmetric coherent information of NC0. So basically, the NC1 is kind of more reliable than NC0. And this is why they are called good and bad channels. Now this channel combining and splitting is again applied recursively. So for two quantum channels N, we have two virtual channels N0 and N1. Then what we do is, like in the next step, we take two copies of these, basically two copies of this box here, and this gives us two copies of virtual channels N0 and two copies of virtual channels N1. Now what we do is we take the similar channels together. So we take N0 together and N1 together. And then again, we do this channel combining and splitting using this Clifford as the channel combining operation. So after two steps, we have four virtual channels, which are denoted here N00, N01, and so on. And again, basically, in the next level of recursion, we take two copies of this basically this box. You see, we take the two copies of this box, and again we put together all the similar channels. So we put together N00 and N10 and so on. And again, we do this channel combining and splitting. So of the third level of recursion, we have eight virtual channels. And similarly, if we can keep doing this, after n level of recursion, we have 2 to the power n virtual channels. And this is our quantum polarization theorem, which is stated in terms of symmetric coherent information. And it says that if we select these Clifford unitaries randomly from the Clifford group, so we select C1 randomly, and then we select C2 and C3 randomly, and C4, C5, so on. You see basically the point here. So if we select these 2-qubit Cliffords randomly from the Clifford group, we have this quantum polarization phenomenon, in the sense that the symmetric coherent information of the virtual channels approaches to either -1 or 1. So the first equation here basically states that the fraction of channels, fraction of virtual channels for which so for any given delta, the fraction of virtual channels for which the symmetric coherent information is between this interval goes to 0. So basically, for almost all the virtual channels, the symmetric coherent information goes to either -1 or 1. And when it goes to 1, basically this corresponds to the useless channels. And when it goes to 1, this corresponds to to almost perfect channels. And the fraction of channels which are almost perfect is given by this equation here. And this is actually twice of the mutual information of the quantum channel. So basically, the fraction of good channels is again equal to the mutual information of the quantum channel. again, we found out that we don't need the whole Clifford group for channel combining operation. We can reduce the channel combining set. So for whole Clifford, for the 2-qubit Clifford group, we have these many elements, 11,520. And what we saw that for quantum polarization, we only need like 9 2-qubit Clifford unitaries. And basically, you can write these 9 2-qubit Clifford unitaries in a simple form. So what we have is like a quantum C0 gate followed by either identity square root G or square root Y on the first wire, or identity square root X or square root Y on the second wire. And these basically this square root X is the square root of Pauli operator X and so on. So basically we can reduce the channel combining set to just 9 Cliffords. Okay, and so now I come back to purely quantum polar codes for Pauli channels. And so a Pauli channel randomly applies a single qubit Pauli on the channel input. So basically, if you have a quantum state rho as the channel input, on the channel output with on the channel output with probability p0, we have so here I represent like sigma identity by sigma 0, Pauli X by sigma 1, and Pauli Z by sigma 2, and Pauli Y by sigma 3. So basically on the output of the Pauli channel, we have basically one of these operations are applied randomly on so this is Pauli channel. And Pauli channel is actually quite similar to a classical channel in the sense that we can associate a classical channel with a given Pauli channel. So for example, here given, okay, so for the given, let's say Pauli channel N, here the associated classical channel is W, whose input and output alphabets are X and Y. And this X and Y is basically the set of Pauli matrices. So you can see this, the classical counterpart takes as input basically this is, you can see this sigma I just as a symbol, like it's not really a matrix, but just as a symbol. So this classical channel takes as input basically a Pauli unitary and outputs another Pauli at the output. And for this classical counterpart channel, so when we send sigma I as the channel input, we receive sigma j with probability pk, where k is like the probability associated with sigma k. where sigma k is the multiplication of sigma I and sigma j. So yeah, maybe it's a bit difficult to follow here, but basically you can see this classical counterpart channel as a symmetric channel on 2 bits. So we can say like sigma 0 is 0, 0, and sigma 1 is 1, 0, and sigma 2 is 1, 1, and sigma 3 is 1, 1. And this classical counterpart channel takes as input one of these symbols and outputs basically again one of these symbols. And let's say if the input is 0, 0, then the first bit is flipped with probability P1, and the second bit is flipped with probability P2, and both bits are flipped with probability P3. Okay, and the quantum polar code for these Pauli channels is actually equivalent to a classical polar code on the classical counterpart channel. So here on the left hand side we have a quantum polar code on Pauli channels. So here these symbols basically represent the Pauli errors that has happened, and we have the Clifford unitaries as channel combining operation, and the red lines here represent bad virtual channels. So for bad virtual channels, we need to freeze their input using pre-series EPR pairs. And for good virtual channels, we can use them to transmit information. What we saw that this quantum polar code on the left-hand side is equivalent to a classical polar code. So on the right-hand side, we have a classical polar code. And the classical channel W here is just the classical counterpart channel associated with the Pauli channel. And the channel combining operation here is not like usual C0 gate, which is used for, usual XOR or C0 gate, which is used for classical polar codes. But this is like a permutation associated with the corresponding Clifford unitary. Now these two polar codes are equivalent in the sense that they polarize simultaneously, and they have the same set of good and bad virtual channels. So for this classical polar code, we also have the same bad virtual channels. Now, this property is kind of useful for the decoding of Pauli channels, and because the decoding in this case can be done basically by doing a classical polar code decoding. So just to summarize, this is how the decoding is done. So first, decoder applies the reverse of the encoding operation, and then does a bell measurement on the pre-series EPR pairs. And this is like an error. The measurement outcome gives an error syndrome. And based on this error syndrome, we can basically do classical polar decoding to estimate Pauli errors corresponding to the good channels. And once we know which Pauli errors has occurred, we can correct the errors simply by applying the respective Paulis. For these Pauli channels, we also have a slightly different polarization phenomenon, which is called multi-level polarization. To recall, like we have shown that when the channel combining operation is randomly chosen from this set of 9 2-qubit Clifford unitaries, polarization happens in like two levels in the sense that the synthesized virtual channels either become completely noisy, either become like completely close to completely noisy or close to completely noiseless. And for the channels that are completely noisy, we need preset EPR pairs for these channels. And the noiseless channels are used for encoding qubits. Now we ask the question, like what happens if we fix the channel combining operations to one of the gates from this set? And we found out something interesting if we fix the channel combining operation to the last gate here. So what happens in this case, polarization happens kind of in multi-levels, in the sense that some of the virtual channels also become half noisy. And for these half noisy channels, their input need to be fixed in either these half noisy channels can also basically cannot be used for encoding qubits. We need to basically fix their inputs in either amplitude or phase basis. And so this is basically this gate here, and square root of y is actually the Hadamard gate, which is quite well known in quantum information. So I will be basically using this circuit from now on to represent L33, this gate here. Now, actually, we can remove the Hadamard gate from this channel combining operation because of this circuit equivalence. So this is like two levels of recursion. So we can see that this circuit is equivalent to this one, and for this one we only need C0 gate, but like for here the control and target, they are not same in each level of recursion. So for the first level, we have the first wire is control, and the second wire is here is as target. On the next level, basically the control and targets are reversed. So basically, for multi-level polarization, what we can do is like apply the C0 gate recursively, like the classical polar codes. But what we need to do is like to reverse the control and target after each level of polarization. And so yeah, basically this looks quite similar to the classical polar codes. And also because we have like two different kind of C0 gates, this gives like a opportunity to optimize in a sense that like, well, like what we can do is like at each level of recursion, we pick between this gamma 1 and gamma 2, the one that basically gives the best polarization property. And by doing so, we can basically increase the speed of polarization. So basically, we don't need to do like go to longer levels of recursion to achieve multi-level polarization. If we do this optimization, we can achieve polarization quite quickly. And this is here just a simulation for a quantum erasure channel. So in this figure, you can see the kind of multi-level polarization. So these, for here we have 16 steps of polarization, and the blue wire here represents the multi-level polarization without optimization, and the red one here represents the one multi-level polarization with optimization. And basically you can see the like a lot of virtual channels for this the blue wire. They are kind of in the middle, like they are not properly polarized, but for this optimal construction, we kind of have, you know, like 3 clear separations. So here we have all the good channels, and in the middle we have half noisy channels, and in the end we have completely noisy channels. Okay, so to conclude, I presented you purely quantum polar codes for quantum channels where polarization happens at the quantum level. And these purely quantum polar codes are entanglement assisted. And we require pre-shared EPR pairs for these purely quantum polar code, and they achieve basically symmetric channel capacity or symmetric mutual information as the rate of information, as the rate of communication. And we have efficient decoding for these codes in case of qubit Pauli channels, and also a slightly different polarization phenomenon, which is multi-level polarization. Okay, so that's all from me. Thank you. And if you have questions, you can ask.
Yes, sir, I would like to ask that I'm not sure if you told this already, but like, how do you exactly like practically tell between which channel will be bad or which one will be good? Like by that 1 and -1, okay, I understand. But like, will the circuit be polarized like up and down, kind of like that?
Can you say it again?
Like, I mean to say that by that information level, you said through that theorem that by
Yes.
that 1 and -1 level, we have good and bad channels.
Right.
But I mean, how practically, how will we tell? Like, will the circuit be polarized up and down, kind of like that?
Okay. Yeah, good question. So actually the polarization, like normally, okay, I will explain using maybe classical polar codes. It's easier. So normally what would you expect that the channels on the top should be very, very bad, and the channels on the bottom should be very good. And in the middle, it's like there is not really a proper order. So it depends on the channel, depends on the noisy channel, but it can be basically determined by running, let's say, some kind of simulation, or basically computing like the reliabilities of these channels. So basically, if you want to like construct the polar code, what would you do is like you order all the virtual channels in terms of their reliability. So which one is more reliable and which one is less? Because of course, if you only have like finite levels of recursion, you will not have like completely perfect channel or completely, bad channels. The channels would be like either close to perfect or close to useless. So what you will do is like you will order them in terms of their reliability, and you will pick, let's say, certain number of channels which are best, like the best in terms of reliability, and then you use them to encode information. I don't know if that's clear. Or...
Okay, I understand. But like that reliability, does that come from the what Clifford gates we're using? So can we like put it in certain fashion that it will be more reliable, or like it is random, does not matter?
So reliability, it's like basically to say like in the sense that like you have generally a parameter to guess like which channel is, let's say, more reliable, and these virtual channels basically are like, they like you need to compute for them individually. So I didn't show like that what are the inputs and output of the virtual channels like in general, but let's say for this one here, you will have this wire as input, you will have all these things as output, and all the previous inputs as output. So basically you have a lot of, the input is a single bit, but the output is like many bits. So what I'm trying to say is like you can basically define all these virtual channels in terms of their input and output, right? And then let's say to judge their reliability, what you can do in theory is like you can compute the mutual information of all these virtual channels one by one, let's say. So if you have mutual information, let's say for two virtual channels, one for which the mutual information is bigger is more reliable, and the one for which mutual information is smaller, it's like less reliable. That is like a less reliable channel. But in practice, you cannot really compute the mutual information of these virtual channels because it's like very complicated expression and would be really difficult. So normally, like people use some kind of channel parameter to estimate the reliability. And it's not really, like, to answer your question, it's not related to the Clifford, but it's like a property of the channel in a sense. You see?
Yeah. Okay, one final question from my side will be that, like currently for error correction, we are like currently nowadays we are really focusing on how much overhead there'll be for the error correction. So what would be it like here, like for let's say some to
okay,
achieve?
so I guess overhead, you mean the are you talking like in sense of fault tolerant quantum computing or
Yeah, yes, yes.
okay. So it's for this one, I only presented like for communication setting, like, so okay, I will try to explain like what's the difference between communication setting and fault tolerant setting. So for in the communication setting, what we have is like the encoding and decoding. And during encoding and decoding, we don't have any errors. And only during the transmission stage, we have the error. But for fault tolerant quantum computing, this encoding and decoding is also faulty. Like basically, when you apply these gates, they will introduce faults. So for this talk, I only consider the communication setting, like only errors happen during the communication, but encoding you can do like perfectly. So for this one, the overhead is basically the, basically overhead means how good your rate of communication is, like the fraction of how many fraction of good channels you can get after the polarization, basically, because you're using the good channels to communicate. So basically the basic important parameter, like the overhead, you can say like the in a sense the right question would be to ask like what is the rate of communication for this one, and the rate of communication is mutual information, which is actually the capacity for entanglement assisted communication. So you cannot achieve better than that in theory, basically. You see or maybe
Yeah. So you mean to say that you are not considering the errors in encoding and decoding. You are basically on the encoded state. You are considering the channel, and on that channel, you are finding out what is the capacity and mutual. Okay.
yes, right.
Yeah. Thank you.
Okay, thank you.
Yeah, thank you, Dr. Goswami, for your wonderful talk.
Thank you. Okay, so
We have lost